Hey guys, this is the third part of the chapter 4 series, and we're doing with remember Newton's first law, which is inertia, right? Just put it up the top to refresh your memory, and tendency for objects, uh, tendency for objects to keep doing what they're doing. So objects at rest want to stay at rest, stay at rest, and objects in motion want to stay in motion. I'm not going to write that for time sensitivity, but uh, just I'm sure you guys know this law by now. So now we're going to talk about well, one thing we did mention in the previous videos was that when a ball, or when any object really, has no force acting on it, it won't go anywhere, right? If it's just sitting on this completely horizontal plane, it's not exactly horizontal the way I drew it, but it's not gonna, because it has inertia, because it has mass, it's not going to move because it wants to stay at rest. That's inertia. And we say that it doesn't move when no force, like if no one's giving it a push or a pull, right? Which is a force, right? If no one's pulling it this way or pushing it that way, it's going to stay at rest because of inertia. But now we're going to go a little bit more into that force aspect. So imagine this scenario. Let's say you have this big boulder, okay? And my friend and I find this boulder, okay? And we walk up, and I walk up on this side, and that's my arm. It's very long because I need to be touching the boulder. And this is my friend. He walks up on this side, and again his arm. Now let's say we both push on this boulder, okay? Let's say I start pushing with 50 newtons, and we define newtons as a unit of force and weight. 50 newtons. Let's say I start pushing on with 50 newtons, this in this direction, and my friend pushes with 50 newtons, okay? 50 newtons. Now this kind of takes us back to that my videos on vectors and scalars, where we kind of try to find the resultant. Right now what we're finding is net force. Net force. And net means total, the total force. Total force, okay? So if we take both these forces, 50 newtons and 50 newtons, and we notice that they're going in the exact opposite directions, and they're exactly equal forces, we're going to say that the net force is 0, okay? And sometimes people put slashes through 0 to differentiate between O's, and I like to do that. So we're going to say that the net force is 0. That's the total culmination of all the forces is the net force, and it happens to be 0 here. But if I were pushing at not 50, if I were pushing at 25 newtons, well, we go back to our vectors and scalars, the net force would be 25 newtons. 50 minus 25 is 25. And the boulder would start rolling this way, right? Because my friend is pushing harder than I am. So that's net force. Now, what does that have to do with inertia, you're going to ask? Well, this big boulder was completely at rest. It didn't want to start moving. When my friend and I came up and started pushing on it, we both applied forces to it. We both applied a push. Both applied a push to it. And so our previous definition of inertia would say, well, okay, there's two pushes going on. It should move. A force is acting upon an object at rest. It should start moving. But no, the net force is what we're looking at here, and the net force happens to be 0, so we can basically say there's no force acting on it. But if we take the second scenario where I have 25 newtons pushing on the boulder, and my friend has 50, he's going to overtake me, and he's going to overtake the boulder, and the boulder is going to start moving. It's going to overcome its inertia because of my friend's 50 Newton force. And so that's what we mean when we talk about net force in terms of inertia, okay? And then we're also going to talk about, along with net force, something kind of important, actually, that I think is really fascinating. I'm going to first give an example, and they do talk about this in your book. I think mostly they talk about it on page 52/53. But let's say I have a pull-up bar, okay? Like, to work out with. And kind of looks like that, and here's the walls, right? Okay, so I have a pull-up bar, and some guy's sitting here or standing here, and he reaches his arms up, very long arms. Okay, and let's say he weighs 150 newtons. 150 newtons, right? Okay, so Sorry about that. So, what we can now notice is that he has two arms touching this pull-up bar, two different points of contact, reaching down to his body that is 150 newtons. So what we're going to notice is that each of his arms is taking 75 newtons of stress, basically. They're taking 75 newtons of a force, half and half, one half and one half of the total of what they're holding up, right? And they're holding up 150. So half of 150 is 75. So now, what happens if he lets go of one of his arms? What happens if this arm just stops holding on? Then this one's going to take one. This one's going to take 150 newtons. That's why if you notice when you're trying to do pull-ups, you can do two fairly easily because each of your arms is taking half of your weight. But if you switch over to one pull-up, it's basically impossible. One arm, it's basically impossible to do a pull-up with one arm because then one of your arms is taking 150 newtons or all of your weight, however much you weigh. And so that's pretty important. The same thing if maybe I'm standing here and I'm standing on two different scales, right? I have scale 1 here and scale 2. They're both going to read half of my weight. So again, if my weight is 150 newtons, again, they don't make scales that measure newtons, I don't think, but this one would, at least like bath scales, this one would read 75 and this one would read 75. This is if I'm putting equal pressure on both of them. If I kind of leaned over on my right side, then this one would jack up and this one would go down a little bit, but that's beside the point. So that's basically net force, because then you'll notice that these two forces always have to add up to my total weight. So if I push down a little bit on this side and maybe this moves up to 90, the act of pushing down on this side is going to decrease this one to, let's say, I weigh 150. This one's going to decrease it to 60 newtons, okay? So that's just because 60 plus 90 equals 150. All right, it always has to equal 150 newtons. That's just how it works. And now we're going to talk about equilibrium. You'll see it here at 4.7. Okay, and they give a little, and it says, a little subtitle is when net forces equal 0. So that's, we kind of talked about that with the boulder example, right? So equilibrium, equilibrium, I believe I spelled that right. Kind of a tricky word. Equilibrium, when net equals 0, right? Okay, so that's pretty simple. We talked about with the boulder. The boulder, when my friend was pushing on it with 50 newtons and I was pushing on it with 50 newtons from opposite directions, the boulder was in equilibrium in the weakest sense of the word. So they give a little definition here, or a little diagram here with a book and a spring on a table, and they talk about something called support force or normal force. Support force. I like to call it support force because it helps me visualize it more, but you can use either. So the support force is basically the force that acts on something, and you cannot really see it. So if my computer sitting on my desk right now, yes, my computer is pushing down. Here, let me draw it for you. Here's my laptop, okay? Or just I'll draw my desktop, okay? Here's my desktop. Let's say it weighs 15 newtons, just for simplicity's sake. 15 newtons. It's pushing down on my desk with 15 newtons. But surprisingly enough, I found this fascinating in physics. When I learned this really got me interested in physics. Surprisingly enough, the desk is pushing up on the computer with a force of 15 newtons, and that's the support force. Support force, okay? And I like to think of it as support because, you know, table, support, it holds things up. So that's interesting. So that's definitely something to think about. And then you'll notice this computer isn't moving, right? It's not falling to the earth or shooting up into the sky because 15 in one direction and 15 in the opposite direction equals 0. 0 newtons, which, as we learned, is equilibrium, right? When net forces equal 0. This computer's in equilibrium. It's not moving, right? So that's definitely a key part of physics that you will need for the rest of your physical science careers. So I found that just fascinating, and I'll see you guys in the homework example section of Chapter 4. Bye.